Welcome back, everybody. Next topic for the day is chemical shift. And before we do that, I just want to go over this concept of shielding that we talked about yesterday. So think about shielding as a mechanism to protect the nucleus from the magnet. If you recall, we have this very strong magnetic field generated by our 600 megahertz or maybe even higher NMR spectrometer. And that magnetic field is going to make an interaction on the excited state of our nucleus. So this will look familiar from yesterday. We have the lower energy state and the higher energy state. And if we have a nucleus in the high energy state, remember we have to have that, by convention, that arrow points down. I messed up, it should be pointing down. There we go. Shielding is when you have electron density that's actually close to the nucleus, and what that will do is it will slightly lower the difference in energy between, say, something that is de-shielded. Okay, and this gets back to, it's all relative to tetramethylsilane, but so shielding and de-shielding is going to, you can talk about it relative to other protons that are in the molecule, and also relative to like functional groups. So the tetramethylsilane, that was the reference material, that is very well shielded compared to other organic compounds, and so that's why that part per million value, it was set to 0. Most things will be de-shielded, and they'll have part per million values that are positive values from 0. So shielding comes about in a silicon-containing species because the silicon actually is less electronegative than a carbon. And a lot of people say it's more electropositive, but it's just two sides of the same coin, okay? Silicon effectively pushes electron density from itself toward the carbon. And in doing so, that makes the carbon more rich in electron density, say compared to a straight old hydrocarbon. And as a result, that extra electron density of the carbon then can actually get transferred into the CH bonds. So the CH bonds, even though they're a couple atoms away from silicon, they feel the effect of the silicon pushing that electron density toward the carbon and in turn toward the hydrogens. And that sets up a little barrier around the proton. Well, not a barrier, but it's just more electron density that's held more closely to the hydrogen nucleus. And the way that I like to look at it as pretty much like the old cartoon Captain America. Captain America has a shield and standing in the way, protecting the nucleus from that strong magnetic field. So if you ever think about shielding, think about it as a protection, just as Captain America can provide to us with his mighty shield. If certain substituents can push electrons toward carbon, then it also follows that there must be other substituents that pull the electrons away from carbon. And that's the example that I'd like to show you today. And this is the more common example in our study of organic compounds. Silicon is really different in that it actually donates electrons into carbon. Let's look at the chemical shift of a series of compounds that differ by the amount of bromine on the carbon. So making a little table here, we'll have chemical shift, and I looked these values up on the internet, so they must be right. And I found values that are rather old because I used carbon tetrachloride as the NMR solvent. So the chemical shift of methane was 0.232 parts per million. And I would imagine they bubbled some methane through their solution to get enough methane into the solution, since methane's the gas. The same for methyl bromide, that's also a gas. And the NMR chemical shift was measured to be 2.682 part per million. So you can see it's actually higher in value for the number. As we increase from methyl bromide to methylene bromide, we see another increase in chemical shift. And now we're close to 5 part per million. Going on to bromoform, we see an even greater value, up to 6.8. So I'm just wondering if anyone knows what the proton NMR chemical shift of carbon tetrabromide is. Totally trick question, all right? There is no proton in carbon tetrabromide, so there would be no signal in the proton NMR spectrum for this compound. Sorry, just had to throw that in to round out the series here. So let's look at exactly why we see this change in value, part per million value, as we add more and more bromine onto our carbon here. Well, the effect is just the opposite of what we saw with silicon. Here I'm going to use X for our halogen, and it could be chlorine, bromine, fluorine, whatever, iodine. We see a very large polarization of that bond, and not so much that we have an ionic bond, but the electron density in that bond between carbon and the bromine is going to want to reside more toward the halogens. So it's going to be like double, or maybe not exactly double, but you've got a compounded effect when you add a second bromine onto the carbon. Now it's like two things pulling away at the electron density that surrounds that carbon nucleus. And for the third substituent, it's even worse. So all of this electron density is being sucked away from the carbon nucleus and residing more closely to the bromines in these bonds. So that kind of has a cascade effect, if you will. That causes the carbon to be electron deficient relative to what it was before all those halogens were added. So it starts maybe in panic mode. It starts taking electron density from the hydrogen. And so the hydrogen no longer has that electron density that it had before the substituents were put on there. And it basically lost the shielding. As the electron density moves away from the nucleus of the protons, we also see a corresponding increase in chemical shift. And if you remember from the first lecture today, every single one of the compounds that I drew here, from methane all the way down to bromoform, will have just one resonance in the NMR spectrum, because every single one of those protons within the molecule is the same. So the chemical shifts across the molecule differ by the differing amount of bromine substitution. But if we were to look at the NMR spectrum for all four of the compounds that have protons, there would just be one peak in the NMR spectrum per compound. I'd like to just talk through an example from your textbook. This is table 13.2. And I'm sorry, I don't have any cursor effects. I forgot to turn those on. But just follow along. It's pretty straightforward. So this is an example of what happens to the chemical shifts of a substituted methane. You can think about these compounds as substituted methanes. What happens to those hydrogens on that compound when you substitute one hydrogen for something else? And the table here, you have the compound on the left. There's electronegativity values of the X, and X is a substituent here. And then finally on the right are the chemical shifts of the corresponding protons on the molecule. So the electronegativity values are the Pauling electronegativities. And biochemists on the course will probably recognize the name Pauling. That's Linus Pauling, very famous biochemist. Won a Nobel Prize for chemistry, and also won a Nobel Peace Prize. I think he's popularly known as the vitamin C guy. But as you guys continue on in your education, especially if you start taking biochem courses, you'll appreciate that Linus Pauling has made some great discoveries and really advanced the areas of both chemistry and biochemistry. All right, so back to the table. Well, let's just talk through the very first example on the table. That's methyl fluoride. And with an electronegativity of 4, that's actually the strongest electronegativity in the periodic table. Fluorine is the most electronegative element, and that's consistent with it residing in that top right corner of the periodic table. So if there's any bond that's going to really polarize when bonded to carbon, it is fluorine. So what happens here is a strong electronegativity deshields the protons that are attached to the methyl group. This is just like we saw with the bromine example. But one fluorine is a lot more potent, if you will, in its deshielding effect than, say, one bromine. And if you scoot down like 4 or so compounds, you can see that the chemical shift of methyl bromide is 2.68. I wonder if that coincides with the value I just gave. You could look at it and see. If it doesn't, it's a solvent effect. We'll blame it on the solvent. But look at the difference. The chemical shift from methyl fluoride, 4.26, and then as you go down to methyl chloride, methyl bromide, iodomethane, methyl iodide, is another name for that compound, you see a decrease in the chemical shift as you work your way down the group in the periodic table. And that is entirely consistent with the diminishing electronegativity of those halogens as you get further and further down the group. It's just a coincidence that the electronegativity of 4 results in a chemical shift of 4.26. Don't read anything into trying to compare like the absolute values of the numbers. This table is to show you trends. And the point here is the more electronegative that you get, the more deshielding you have for the protons that remain on the carbon. And there's a halogen series, and you can kind of see how oxygen kind of rates, if you will, in its electronegativity and its electron withdrawing power. It's not as good as fluorine, but a little bit better than chlorine. And that's also consistent with oxygen's position in the periodic table. It's a little bit to the left of fluorine and one row above chlorine. The bottom 2 examples are interesting because it just shows you how much more shielding the silicon is relative to a carbon. So here we're looking at tetramethylsilane, which by definition is 0, and comparing it to a compound that had carbon in the center. And the compound that's, it'd be like a little plus sign with carbon right in the middle, that's neopentane. So neopentane, the carbon does not have any kind of shielding effect relative to silicon. So it's just another carbon, and we see a chemical shift that's 0.86 ppm. And this example here is just to show you that silicon is less electronegative than carbon, and as a result, we have less of a electron withdrawing effect of that center group. just want to briefly look at the effect of hybridization on chemical shifts. So this is another table in our textbook. And the point here is that when you have protons that are near to carbon-carbon double bonds and carbon-carbon triple bonds, there is an effect. And it is going to really depend on exactly the chemical environment of that proton. The vinylic protons are the ones that pay attention to these, okay? These are in a fairly large ppm value. These are substantially de-shielded relative to others. And it's got to do more with just hybridization, and the textbook goes into a little bit more detail about why that's so. But for your purposes, just understand that vinylic protons, those are protons bound directly to a double bond, are going to show up in this region in the NMR ppm scale. And the acetyletic, they vary, and of course it varies by what R is, because R has an effect on the whole molecule. So depending on what R is, these can range between 2 and 3. And that's kind of in line with the allylic protons as well. But the electronegativity of oxygen has a much greater control, if you will, a greater effect is what I should have said, a greater effect on the chemical shift. So this hydrogen here is asking for, the reason why this is in a table is because it gets you to think about, okay, this is a hydrogen bonded to a carbon that's double bonded to something else. And when that something else is an oxygen, there's a pretty big chemical shift relative to TMS, close to 10. This is really at the far left of your standard NMR scale. Where with a vinylic, let's just say instead of oxygen here, that was CH2. With a vinylic, then you're only about halfway there. You're between, around 4.6 to 5.7. So that's the point here. All right, now we got to talk about benzene. It's been a while since we talked about benzene, so we're going to talk about the NMR of benzene. Here's a figure from our textbook. This is figure 1311, and it shows how benzene is affected by both the applied magnetic field as well as a magnetic field that is present in benzene due to the delocalization of that pi electrons. And I had this eureka moment as I was getting ready to describe this to you. This is why we talk about aromaticity first, so that you can appreciate this principle right here. Because we talk about aromaticity and then we move into instrumentation, and then we talk about, later on in the course, we're going to get into all these reactions of aromatics. But you have to understand aromaticity first so you can understand this figure. So it's all been for figure 1311. Remember how I showed you in my first lectures how those electrons in the pi bonds that are formed by the combination of p orbitals can basically circulate all around the top and the bottom of the molecule, and all those atoms that lie in the plane, that's called the sigma framework because it's made up of sigma bonds. So the pi bonds are flowing around in this circular motion, or at least they can, and whenever you have a flowing particle with charge, it's going to generate a magnetic field. This is Michael Faraday again. Movement of an electron generates a magnetic field. So imagine a circular flow of the electrons around the top of the ring, and you can also have it in the same situation in the bottom of the ring. These are those electrons in that pi bond. That generates its own little mini magnet, if you will. So there's magnetic fields that kind of emanate from the center of the molecule and swirl around, just like they do on our planet. Remember that picture of the planet and the Earth's magnetism? So benzene has its own little magnetic field with its own magnetic lines. And in doing so, it actually will align with the applied magnetic field. So now you have two forces that are interacting with each other constructively. And this is what they call the induced local magnetic field. Local means, within the molecule. And then that applied magnetic field is reinforced. So you are actually kind of moving up in energy, and that causes a de-shielding effect of these protons. And just remember that the higher the ppm value, the higher the energy, and the more de-shielding that you have around that particular nucleus. So due to this effect here, this is the induced magnetic field effect. Also, it's got a really fancy name. The movement of the electrons is called a ring current, and this effect is called a diamagnetic effect. And definitely pay careful attention to this as you review chapter 13. I think I will ask something about this at some point in this class on a problem set or an exam. But this explains the chemical shift of benzene, which I'm going to show you in a moment. So here we have it, benzene, C6H6. So a couple things here. First, look how simple the NMR spectrum is. We only have one peak. And that makes perfect sense, right? Based on equivalent hydrogens. I think one of the first things I told you guys is that every single hydrogen in benzene is the same. Every single carbon-hydrogen bond, same length. And you know why that is, of course. And so every chemical environment of these protons on the benzene ring, they're all identical. So one peak makes perfect sense based on the structure. And look how de-shielded this particular resonance is. All the way down, the actual value here is around 7.339 part per million is what I have. And this is, of course, relative to TMS. But I noticed that there isn't any little peak for TMS here in the NMR spectrum. And that's likely because they reference this spectrum in another way. Maybe whatever solvent they used. I think the solvent was deuteriochloroform. So somewhere at around 7.25, there's probably a little bit of a peak due to that chloroform resonance, CHCl3. Small amount of residual chloroform in the CDCl3 is likely how they were able to figure out that this resonance was 7.339. But just hearkening back to what I was saying in the previous slide about why is this compound resonating in this NMR spectrum at such a high ppm value. And it's just due to that induced magnetic field that happens when you have circulating pi electrons. So the word of the day, I think, this will be our word of the day, is diamagnetic effect. All right, so this is really how you start impressing your friends. This is the diamagnetic effect that causes de-shielding of the protons in benzene. All right, one last slide and then we'll call it a day. I've erased all of the markings on the NMR spectrum of benzene. And I did this so I could just talk about some terms that are used to describe the x-axis of an NMR spectrum. The y-axis doesn't really have any units. It's kind of common just to make the largest peak fill the whole height of the page. And units really aren't any of any value just in terms of the intensity of the peaks. We're going to learn tomorrow all about integration And there you'll see the value of putting physical numbers to these peaks. But for now, let's focus on the scale one last time. So at the very right-hand side of the spectrum, we're going to have our ppm scale starting at 0. And certainly if you have peaks that show up in the negative, they'll be there. You just have to know to set your spectrometer to another setting so you can go down there and look for them. In fact, some of those cyclopropanes that I studied in graduate school had very low ppm values in the negatives. But that's another story for later. So with respect to the shielding and the chemical shift, low chemical shift is expressed in delta, and it's going to start at 0 on the right-hand side of the scale, and at the high chemical shift, that would be on the left. And it's possible, just as you can go lower than 10 for your NMR signals, it's also possible to go higher than 10. And we'll have some examples of chemical shifts that are in the higher region, 15 part per million or so, for carboxylic acids in particular. And the other thing is frequency. As we increase in part per million, we also increase in frequency. And I showed you an equation yesterday as to how to calculate those two. So you may want to have another look at that. Familiarize yourself how part per million and frequency are related. High frequency is high energy. That comes from that famous equation, E equals h nu. So as we go toward the left on our NMR spectrum, we have higher energy values for the resonances. And that relates back to this whole concept of shielding and deshielding. Remember Captain America? When we drop the shield, we lose the protection. And as a result, the deshielded protons are going to require higher energy to get them to resonate, because they are no longer protected by the electrons that are held closely. And the last thing I want to mention, and we're not going to use these terms, but I'm going to point them out in case you hear them in passing, likely from people that are much older than me. There used to be a description of the NMR ppm scale as low field and high field. And field here actually relates to the strength of the magnetic field. That old instrument that I described that you plugged into the wall and generated an electric field with an electromagnet, that instrument was called a continuous wave instrument, as opposed to a Fourier transform instrument, which corresponds to that nice brochure photo that I showed you with the technician not wearing safety glasses in front of it. But the old continuous wave instruments were called continuous wave because they would be pulsed at one frequency, 60 megahertz. So 60 megahertz frequency would be pulsed in order to see if there was any resonance there. But in order then to change the frequency ever so subtly, what they would do is change the field of the magnet. And that could be done by like adjusting the electricity that ran through the coils to make the electromagnet. So low field is going to be higher frequency, and then high field would be the low frequency region. And again, these are antiquated terms, but you might see in journal articles or maybe some people talking about NMR, hey, check the low field region. What that means is the high frequency region, the high ppm region, where the deshielded protons are going to reside. Alrighty, another big bombardment of information today. It's a lot, I know. Stay on top of things. Definitely read the chapter very carefully in your textbook on NMR spectroscopy. Tomorrow we'll finish up with the theory in discussing spin-spin coupling and integration. So have a good day, everybody.